JUnit Extension Model, Lecture 6. Writing Custom Extensions. JUnit 5 provides an excellent extension model that enables the software engineer to write custom extensions into the unit test flow. Just like the decorator pattern around methods and other extension points, or very similar. This extension model allows you to write such tests as add-parameterized test or add-repeated test. In fact, these annotations are made possible by this extension model. These annotations rely on built-in extensions though, not custom extension, but it has the same model. There are several extensions built in that JUnit uses out of the box, and others that you can write yourself if you need to customize how tests are processed by the JUnit runtime. Quite nice. Obviously, before one writes an extension, one must clearly understand the need for it. Otherwise, maybe a simpler path is easier. Let's get started with the JUnit extension API. This lecture will instrument your extension writing knowledge to the point where later in the lab, you will write an extension that reports during a unit test run how much time the unit test took to run, and also how much time all unit tests in a test class took to run. Quite sensible stuff to measure. You will implement it in the lab which follows this lecture in order to do a hands-on task, so be sure to do so. First, let us see all the extension points offered by the extension API. They are quite extensive, no pun intended, and they are listed in the next slide, so please spend some time familiarizing yourself with them and writing them down. The basic extension points available to you are: the number after specifies the order of execution for clarity. Before all callback, and I'm gonna give you 10 seconds to write it out. So that was number 1. Add before all, number 2. And that is implemented by lifecycle method execution exception handler, method name handle before all method execution exception. And I'm gonna give you 30 seconds to write out that mouthful. Of course, the add before all is the built-in extension point. It's already there. And the lifecycle one at number 3 is the true extension point, and it lets you capture exceptions propagating from the add before all annotated methods. Number 4 is before each callback, and I'm going to give you 10 seconds. Add before each is at number 5, and lifecycle method execution exception handler and method name handle before each method execution exception at 6 lets you capture exceptions thrown by add before each method. And I'm gonna give you 30 seconds to write out the lifecycle mouthful. At number 7 is before test execution callback, and I'm gonna give you 10 seconds to write it out. Okay, let us continue. Add test is at number 8, and test execution exception handler at number 9, and I'm gonna give you 15 seconds to write out test execution exception handler, which lets you capture exceptions thrown from add test method. After test execution callback at number 10, I'm gonna give you 10 seconds to write it out. Add after each at 11, which is a lifecycle method, so this list is a mixture of lifecycle methods and extension points. At 12 is the lifecycle method execution exception handler, handle after each method execution exception. And I'm gonna give you 30 seconds to write it out. Okay, so this number 12 extension point lets you capture exceptions. Let us go. At number 13 is after each callback, and I'm gonna give you 10 seconds to write it out. At number 14 is add after all, lifecycle annotated methods. And at number 15 is the lifecycle method execution exception handler and method name handle after all method execution exception. And I'm gonna give you 30 seconds to write it out. Next, at number 16 is after all callback. I'm gonna give you 10 seconds to write it out. Let us continue. So overall, there are 16 method executions in total. 5 of them are parts of the normal execution flow, and 11 of those you can implement in order to modify the execution flow, that is, to extend the JUnit runtime. So out of the 16 points, 5 of them are lifecycle, 4 of them are lifecycle methods, 1 of them is the actual unit test method, and 11 of those are extension points. So in some cases, as evident above, extension points only allow you to intercept exceptions thrown. In others, they are full-fledged extension points where your code could do some interesting things. And there are class-level and method-level extension points. Class-level extension points are those which apply to the entire test class, and method-level extension points apply to the unit test method or methods. You should study all of these extension points and try to memorize them. And you absolutely should take part in the lab following this lecture in order to get hands-on experience in developing an extension. It will be invaluable for you. Once you develop an extension class using the extension points in the previous slides, you can register it with the JUnit runtime in 3 different ways. Way number 1, declaratively, by using @extendWith annotation. For example, @extendWith class name.class, and that's a fully qualified class name or just the class name, depending on whether you import the package. And that is applicable either at the class or method level. If multiple extensions are registered, they run in the order listed before the test and in the opposite order after the test. In effect, they wrap each other. In addition, class-level extension points can only be used in your extension if you annotate a test class with it. Obviously, for a test method, its extensions run first, then, if any, inherited parent method extensions, if it's a subclass. Then, test class extensions for the class in which the method resides. Then, its parent test class extensions. You get the picture. But make it as simple as possible and always log what your extensions are doing, or you'll get messed up. Well, the second level to declare an extension is programmatically by using the @register extension annotation, applicable either to an instance variable or to a static variable. If via instance variable, the running order is deterministic to ensure repeat runs are the same, but not obvious to you, unless you force it to be explicitly ordered via the @order annotation. And if you mix ordered and unordered extensions, if you declare more than one, ordered ones whose order is less than integer .max value divided by 2 will be run before any unordered ones, and then, should you have ordered ones with order value greater than integer .max value divided by 2, they will be mixed in with unordered ones and will run in a repeatable but non-obvious order, as if they were unordered to begin with. Weird stuff, complicated stuff this is. So either do not order your extensions or order all of your extensions, and don't write too many extensions and don't overcomplicate things. And you can see why. If via static variable, they are registered after any other extensions registered with @extendWith annotation. And they also can implement both class level and method level extension API. They are class level. These variables cannot be private and they cannot evaluate to null, whether method level or class level. And automatically via Java's service loader mechanism, that is the third way to register an extension, by using the java.util.service loader class. These extensions are registered globally after JUnit's built-in extensions. So to force automatic registration of extensions, take a look at the next slide. And to rehash, we have covered declarative registration of extensions with the @extendWith annotation. We covered the programmatic registration of extensions with the @register extension annotation. And now we are covering the automatic registration of extensions via Java service loader mechanism. So quite a few varied and diverse ways to register extensions. So you can register extensions automatically. Let's go back to the third way to do it. In order to do it, add the fully qualified name of the extension class to a file named org.junit.jupyter.api.extension.extension and place this file in the metainf/services folder of your jar file. It will be picked up from there, and what you will include there will be registered automatically as an extension. So I'm gonna give you about 15 seconds. Please write out org.junit.jupyter.api.extension blank file, so you don't confuse it with a property. Then set the JUnit.jupyter.extensions.autodetection.enabled parameter value to true by adding this line either to JUnit-platform.properties file or by adding it at runtime via Java virtual machine property d JUnit.jupyter.extensions.autodetection.enabled equals true. And I'm going to make about 40-second pause to enable you to write out first the property as you would put in the properties file, and then to write out the JVM property with the -d preceding it. So these are the three ways of registering custom extensions in JUnit. Also, if you register an extension twice, only the first registration will be picked up. Any other ones will be ignored. In addition to basic extension points, there are a few advanced extension points which allow you to do pretty interesting things with the testing workflow, such as integrating with third-party frameworks, injecting parameters, etc. They're indispensable to get advanced stuff done with extensions, and you should look at them no less carefully than at basic extension points, because you're getting that good. Well, yes. The advanced extension points are execution condition interface, which permits you to specify conditions and after which the unit test to unit tests will run or not run. If multiple implementations of execution condition are registered, the one which returns true for do not run causes others not to run, akin to short-circuiting OR operator. So I'm gonna make a 15-second pause for you excuse me, to write out execution condition. So let's go on. You can deactivate conditions by setting the property JUnit.jupyter.conditions.deactivate to a literal or irregular expression specifying which conditions should be disabled and not applied. You can put this property into the JUnit-platform.properties file, use it as a runtime JVM property or as a configuration parameter in the launch discovery request being passed to the launcher class, to be looked at later in the next lecture. So I'm gonna make a 15-second pause for you to write out JUnit.jupyter.conditions.deactivate. Let us look at other advanced extension points in the following slides. The test instance factory interface should be used when you need to create test class instances. That is quite a powerful extension, And I'm gonna make a 15-second pause for you to write out test instance factory. You can get a test class from a dependency injection framework or by using a factory method. These are some common use cases where you would implement this interface. And obviously for all these advanced use interfaces, we're going to look at them in the lab because they're next to impossible to comprehensively explain in text. You have to actually work with them. If this extension is not registered, JUnit runtime will go ahead and invoke the test class's constructor. If the constructor expects arguments, it makes sense to register another extension called parameter resolver. And I'm going to make a 15-second pause for you to write out parameter resolver. Let's look at this extension in the next slide. The parameter resolver interface assists you in injecting a parameter into a test class constructor, a lifecycle method, or a test method. And obviously it is a very powerful concept, very versatile and flexible. There are some built-in parameter resolvers, such as testinfo parameter resolver, which injects an instance of the testinfo class. And I'm going to make about a 15-second pause for you to write out testinfo parameter resolver and testinfo. And testinfo class, as an aside, is a class that has some pretty interesting information about the running unit test. And you may register your own custom parameter resolvers. Parameters may be resolved by name, type, annotation, or some combination of those. And parameter resolver interface uses the parameter context class to do its lookups of parameter values. And I'm going to make a 10-second pause for you to write out parameter context. We will see we will see examples of this advanced extension points in the lab following this lecture. Your attendance is essential because this topic is what separates intermediate practitioner from advanced practitioner, which is proficiency with the extension model. The test watcher interface is another interface of interest. It provides methods that help you process the results of test method execution. And so I'm going to make a 10-second pause to ensure that you write out test watcher. Add test or add test template methods qualify as test methods in the context of this extension point, so it can be applied to both types of methods. Extensions implementing this interface can be both class level and method level. And it has methods test disabled, test successful, test aborted, and test failed. And I'm going to give you about 30 seconds to write out all of these four methods, just in the most basic form: test disabled, test successful, test aborted, test failed. So these are the methods that second lifecycle events of the unit test of the same ilk. So let us now rehash the advanced extension points for the extension model, which are execution condition, and I'm gonna give you about 15 seconds to write it out again. So execution condition, and I apologize for switching this slide. So it disables or enables test methods based on a condition. The next one is test instance factory, and I'm gonna give you about 15 seconds to write it out. So this interface creates your own instances of test classes according to your needs. Next is the parameter resolver interface, and I'm gonna give you about 15 seconds to write out parameter resolver. So this interface specifies how parameterized test class constructors, lifecycle methods, and test methods, which have parameters, receive their parameter values. Last but not least is the test watcher interface, and I'm gonna give you about 10 seconds to write out test watcher. This interface specifies how results of a test method run are handled by the JUnit runtime. So it is a great idea to have these advanced extension points memorized, and in a couple of slides we are going to look at how information is communicated between extension points by being stored in the store object, which is little more than a simplified java.util.map. The invocation interceptor interface provides an extension point where you wish to intercept a test method, perhaps to never call it, perhaps to modify the call, and I'm gonna give you about 10 seconds to write out invocation interceptor. This interface provides a fairly complex API that you should familiarize yourself with, and it will be obviously mentioned in the lab. This interface is very powerful because it hands you all sorts of opportunities to alter how the test method runs. Use it with care. Every method in an extension is supplied with the extension context class that enables the method's awareness of the broader context or surrounding within which it is running. And so I'm gonna give you about 10 seconds to write out extension context. There is the store object associated with each extension context that the extension can use to keep state in the current extension point invocation. And I'm gonna give you 5 seconds to write out store. Extension class is instantiated only once per test session, not once per test run, so the store object is the only way to keep state, and that is why it is needed. Extension context.store.closable resource. Implementing classes are automatically closed when the relevant extension context goes out of scope by having their close method called, but they have to implement the closable resource interface. And I'm going to give you 15 seconds to write out extension context.store.closable resource. Extension context.store.closable resource. Implementing classes are automatically closed when the relevant extension context goes out of scope by having their close method called, but they have to implement the closable resource interface. And I'm going to give you 15 seconds to write out extension context.store.closable resource. Extension context classes have progressively broader scopes, from method level to class level. In fact, to illustrate, a method level extension context class's parent is the class level extension context class. So next, we will look at utility classes provided by the extension model. These classes simplify implementing custom extensions. Let's look at the next slide. So these utility classes are very useful because they provide a lot of boilerplate functionality that you might want. The first one is annotation support, and it provides static methods to discover and work with annotations placed on test classes or test methods. Now I'm going to give you about 15% to write it out. Annotation support. Class support class provides static methods to work with class objects, and I'm going to give you about 10 seconds to write out class support. Reflection support class enables support for runtime discovery and manipulation of runtime code via static methods. I'm going to give you about 10 seconds to write out reflection support. Modifier support class allows you to work with member and class modifiers via static methods. And I'm going to give you about 10 seconds to write out modifier support. So to rehash, they are annotation support, class support, reflection support, and modifier support. Let us go on to the next slide. So add before all and add after all methods on a superclass are run before and after respectively, those methods on a subclass. Add before all and add after all static methods on an interface are run before and after respectively, corresponding methods on an implementing class. Add before each and add after each methods on superclasses are inherited by subclasses as long as they are not overridden, and they run before and after respectively such subclass methods. And so this is our study of the inheritance behavior of our lifecycle methods. Let us go on. Add before each and add after each default methods on interfaces are inherited as long as they are not overridden, and run before and after respectively the respective methods in an implementing class. Recall that multiple same annotated lifecycle methods run in an order that is deterministic but not obvious to you, and same annotated lifecycle methods within a test class do not wrap. Let's check out the last slide of this lecture, the conclusion. Do undertake the lab. This lab is crucial to your status as an advanced practitioner of unit testing with JUnit. So in conclusion, JUnit 5 provides a new extension model that was not there for JUnit 4, and it does so to make modifying how unit tests run easy and streamlined. This model works by exposing a set of extension points that you can insert your code into, and thus you can modify the workflow of the unit test or the test class. So the extension model is a powerful new addition to the JUnit toolbox, and you absolutely must master it to gain the most out of this course. So I'll see you in the quiz, and I'll most definitely see you in the lab. Good luck.